Hello friends, in this video I will explain about paired and pixel detectors in high energy physics experiments. Since we all know that paired and pixel detectors are highly useful in high energy physics experiment to measure the position of the particle. So what is a paired detector? So paired detectors are typically of the millimeter by millimeter size sensors. So in this case the area is of the order of millimeter square and the thickness can go from 50 micrometer to 300 micrometer. So we can use many paired detectors to measure the position of the incident particle. Suppose we have the incident particle here, let's assume it's a proton, then we have the size of the proton of Fermi meter, and we are measuring this point using the paired detectors, which is of the order of millimeter. So in this case the center position, the position of the particle is given by the center position of the fired pad along the x-axis and along the y-axis, and the uncertainty depends on the size of the pad. It's the similar things if you measure the some length using this scale. In this case the uncertainty depends on the least count of this scale, which is of typically of 1 millimeter. If you have many pad fired in this case, then if you are using the charge center of gravity method, then the spatial resolution depends on the signal to noise ratio. If you have large signal to noise ratio, then your uncertainty in the measurement will be smaller. So that's why we want large signal to noise ratio. So pad detectors are used to measure the two coordinates. When suppose this pad is fired, then the position of the particle is given by the center position along the x direction and the y direction. And we have the small material budget because we have the small thickness, and the error in the position measurement is large because the size of the pads are large, like typically of millimeter, and the capacitance is large because your area is large here, and then you have a large capacitive noise, and then that can decrease the signal to noise ratio. And then if you have this number is small, then you have the large uncertainty in the measurement of a position. And here we have a less number of channels than the pixels, so we have a less power consumption. Suppose we have the active area of 5 millimeter square, and then we have a 1 millimeter by 1 millimeter pad. Then we have only 5 pads. That means we have only 5 channels. These are useful when we don't want good spatial resolution, because we have large size pads, and but we want a very good timing information. So these are used in the CMS experiment. LGAT pad sensors are used in CMS experiment at the MIP timing detectors, and the high granularity timing detectors in the Atlas experiment. Now in the recent improvement, AC LGAT technology also developed, which can provide the good spatial resolution as well as the timing resolution. If we want good spatial resolution, then what we have to do, since we have to reduce the size of the pads, basically there it comes to the size of the pixels, which are smaller in size. So pixels are typically of the micrometer square area sensors. So we can use many pixels to measure the position, as I explained before. So in reality we have many pixels on the wafer. So you can see these are created by photolithography method, and each pixels we can read the signal. So we have a channel for each pixel. So this is the configuration. So there are several advantages of using the pixels. It produces unambiguous hits because pixels are independent, and we don't have any issue of ghost hits, which is basically in the case of strips, which I will explain in my next video. And the area of pixel is small because your area is small, and so your capacitance is small, and capacitance is small means capacitive noise is small, which will improve your signal to noise ratio, and that will improve your spatial resolution again. And pixels have very small volume, and so we have a small leakage current, typically of the order of picoampere. And the disadvantage of you have a larger electrical connections. Suppose you have n pixels in this direction, n pixels in this directions, then you have the total pixels n square, so that corresponds to n square connections. So we have a large connections here. So electronic cooling is required for the working of the detector. and it requires large power consumption because we have a large number of pixels and n square pixels for an area. Suppose in the previous example, as I mentioned, that let's assume the area is again 5 millimeter squares, and the typically pixel size is assumed, let's 100 micrometer by 100 micrometer. Then you have a 500 pixels here, while you have only 5 pads here, so you have 100 times more channels here. So that's the disadvantage of using the pixels. So we have a large number of channels and a large power consumption. Typical size of the pixels we use of the 10 micrometer by 10 micrometer in the future, but currently people are using in high energy physics 50 micrometer by 50 micrometer pixels. So in my next video I will explain about the more details about the strip detectors, single-sided as well as double-sided detectors, and what are the advantages and disadvantages where we have to use these types of configuration. This configuration is also used by many experiments, so I will give a more detail about it in my next video. Okay, thank you.